Welcome back to Project Pulse. In the previous lesson, we implemented the cash sweep mechanics into the model. In this lesson, we will model another core lender metric, the Loan Life Coverage Ratio, or LLCR. Conceptually, LLCR answers a simple question. If I discount the remaining CFADS over the remaining loan life, how many times does that present value cover the debt outstanding today? So it's a longer term coverage view compared to DSCR, which is period by period. Now watch what happens when I switch to the full cash sweep case. Once the sweep kicks in, the loan balance gets paid down faster, and that directly improves LLCR, because when we take the present value of remaining CFADS, we are dividing by much smaller outstanding debt after the sweep has done its job. If you're new to this Deal Lab series, I recommend starting with part 1, where you can download the model start file for free and build the model alongside me. Link is in the video description below. Before we jump into Excel, let's briefly talk about the loan life coverage ratio. LLCR is calculated as the present value of CFADS over the remaining loan life, divided by outstanding debt. The key idea is the present value part. We discount future CFADS using a debt discount rate, typically the weighted average cost of debt. In project finance, LLCR is a confidence metric. It tells lenders whether the project still covers the loan when you look forward over the remaining debt tenor, not just the next period. It complements DSCR. DSCR is short-term resilience, LLCR is longer-term capacity. Practically, LLCR influences structuring and credit comfort, especially when revenue is more volatile or when mini-perm features exist. And it's also useful for monitoring. If performance is worsening, LLCR is a fast way to see how much cushion remains. And now let's move back to the model checkpoint file from our previous lesson. In the previous lesson, we have integrated the cash sweep right here. And what we'll cover in this lesson is the calculation of the loan life coverage ratio. And the first thing we will need to determine is the discount rate that we will use to discount our CFADS. And that is most typically the weighted average cost of debt. And we could either pull in our all-in interest rate right here in row 608, or instead we can back solve our weighted average cost of debt by actually taking our interest expense and dividing it by our term loan outstanding. So to do this, we will implement an if error statement in case we divide by 0. And then we will scroll up and look for our actual interest expense. And for LLCR calculation purposes, we will use our interest expense including our base rate sensitivity. So row 573. Let's take this interest expense and we will divide this by, scroll up, our term loan balance. And now it's important that we divide by our balance brought forward and not by our balance carried forward. And why is that? Because in, say, year 2026, at the beginning of the year, we will have $125 million term loan outstanding. And in this model, we assume that the repayment occurs at year end. So that means during the full year, we must have paid interest on the balance brought forward and not carried forward. So let's divide it by 553 and comma, if that's an error, we want a 0. Hit enter. Let's drag this over, Control R. And for the first period, we get 5.88%. Then if we scroll up, that actually aligns with our all-in interest rate, both before and after sensitivity, because we haven't sensitized anything. And this is just a way of back solving the actual cost of debt instead of just pulling in our interest rate. And the next thing we'll have to do is determine a discount factor multiple as well as a PV discount factor. And this is very similar to our debt sizing approach from a previous lesson, where we took a similar approach to determine our final term loan size. So conceptually, we are going to implement the same logic for determining the LLCR. And let's start with our discount factor multiple. For this one, we pick up the previous period's factor, and we'll start with 1 or 100% in J609. So that's a technical input of 100%. Kind of works like an index. And then we'll multiply this with 1 plus our periodic cost of debt. So in the first period, that's 0. And then we'll multiply this with the maximum of either, let's scroll all the way up, our financial close flag, because we want to make sure that it's actually turned on in our very first period, which is our financial close. Hit F4 2 times. And the second number is our term loan flag. So scroll down to our term loan section, and that is in row 517. And we take the maximum of these two numbers because, as you can see, in 2025, the term loan flag is off because our term loan is actually just drawn in 2026. Or better, this is when our repayment period starts. Let's hit F4 2 times for this one as well. Close parentheses, hit enter. Drag this one over, Control R. And that basically gives us an index that we can then use to determine our PV discount factor. And to do this, all we have to do is take 1 and divide it by our discount factor multiple. And to avoid getting an error, we will do an if error statement again. So if error, and we will take 1 and divide 1 by our discount factor multiple, 609. Close parentheses, comma 0 in case there's an error, close parentheses, hit enter, and let's drag this one over, Control R. Now this is the PV discount factor that we will then use to multiply our CFADS with. So in the first period, we will discount them with approximately 94%. And the CFADS in the future are discounted by a higher factor. So in 2034, for instance, we'll have a factor of 59%. And once we have this PV discount factor, we can pull in our relevant CFADS. So let's first find our CFADS during our debt term. And we have modeled that before, so that should be a simple linkage. Scroll up, search for our CFADS. And what we will want to do is to pick up the CFADS during our debt term. So we want to make sure that we are not accidentally picking up the CFADS during the full financing tenor, because the LLCR assumes that the CFADS are only considered during our actual term loan tenor. So make sure you pick up row 490, hit enter, drag this one over, Shift Control R. And now to fully conceptually get the calculation of the LLCR right, we also have to do an adjustment for our LC interest expense. And our LC interest has not been modeled yet. This is something we will do in the next lesson. That is in row 664. However, if we scroll up, you will notice that in our total debt service, we have already pulled in our DSR LC interest in row 580. And why do we have to adjust by our DSR LC interest? That is because if we scroll up to our CFADS during the debt term are coming from here, and our EBITDA in 399 does actually not yet consider any DSR LC interests. We can also see that in our integrated financial statements. So the DSCR LC interest is actually kicking in row 75, and the interest on our letter of credit will actually be paid kind of like an OPEX item, which means that for term loan sizing purposes, we excluded the DSR LC, which we did in row 524. So we adjusted for sizing purposes by our LC interest payable, because the LC interest reduces the term loan capacity that we have for our term loan, and the LLCR is a pure term loan metrics. And since we have reduced our CFADS by our LC interest after considering our DSCR sizing ratios, we will also have to adjust this DSR LC by our sizing ratio. So essentially the LC interest just reduces our overall CFADS slightly. And since it's a reduction, we will model this negative minus if error. And the LC interest we can pull in from row 580, which is currently 0. And then we will multiply this with our DSCR including sweep. So our DSCR essentially reflects the target ratio at which we have sculpted our debt. So not only do we have to consider our DSR LC interest, but we also have to adjust it for the actual target DSCR factor that we use for sculpting purposes. That's why we multiply by our actual DSCR output from the live model. Comma 0 and hit enter. Let's drag this one over, Control R. For now that's 0, but once we have modeled our DSR LC, that will kick in. And then our LLCR relevant CFADS is basically just the sum of those two rows here. Drag this one over, Control R. Actually hit Control Z, let's do this again. Copy this and Alt H VSF for pasting special formulas only, so we keep our formatting. And now it's going to be slightly tricky for our NPV of future CFADS for our debt term. So let's implement this formula in a specific period, say 2028. And here we'll have an if error statement again. If error, and we will open another parenthesis and use a sum product function. Sum product. And right now we are in the year 2028. And what we want to consider right now is the forward-looking CFADS for the next periods. So we pick up our LLCR relevant CFADS in the next period. Then we mark everything up to the end of the model, up to AT, and we will only fully anchor the end period so that this reference here isn't moving further to the right. So fully anchor only the right part. The left part we want to move as we drag the formula along. And these are our CFADS, and we'll want to multiply our CFADS in the respective period with our PB discount factor. And this is why we use a sum product function. So we take the same length for our PV discount factor, mark all of these cells here, and again we only fully anchor the second reference point, hit F4 once after clicking into AT610. And once we multiply these two values with each other, we have the sum product of the future outstanding CFADS discounted to today. And in this case, today is close parentheses divide by, today will be in year 2028, which means we have to divide by the discount factor in that specific period. So that will be N610 for the year 2028, because we are not generating the net present value as of today, meaning financial close of the model, but instead we want to understand what the loan life coverage ratio would look like if we were in the year 2028 and would then look forward into the future based on the CFADS at the time. That's why we have to adjust the net present value by dividing the time value of money in this specific year. At first, this might seem slightly complex, but it's essentially just basic time value of money principles. Close parentheses, and if this returns an error, we want a 0. Close parentheses, hit enter. Copy this, paste it here, and let's drag it all the way over, Control R. And you might notice that right now we are still in the live case 21 which is our full cash sweep case, which is the reason why our LLCR improves so much in later periods. Now let's see what that same case would look like under case 18. And here you will see that our LLCR starts out right around our contracted DSCR metric of 1.3 and then slowly gravitates towards the DSCR of our merchant sizing target of 2.0. And just conceptually that you understand what we're doing here, the formula has already been implemented. So what we just do here is we take our NPV of future CFADS in that period and divide those by our balance carried forward of our term loan. And that's basically the end of period outstanding debt balance. And at the end of this period, for instance, we want to understand how much future CFADS on a net present value basis are sufficient to repay that debt balance. And in this case, it's a 1.41x multiple, which increases slightly as we gravitate toward more merchant tail revenues when it ultimately plateaus at that DSCR sizing metric. So to even further understand how DSCR and LLCR correlate, let's switch over to case 1, which is our full tolling case. And here we sized our debt based on a 1.3 coverage ratio. So let's execute our macro. Scroll back down and you can see that our DSCR is at a 1.3 flat. And let's see what our LLCR does. Our LLCR starts off very similar to our DSCR at around 1.3 and then naturally gravitates toward a 1.96, which you will notice is our end of period DSCR, our actual DSCR. So the loan life coverage ratio will naturally gravitate toward the end value of the DSCR if we use a flat DSCR sculpting profile. And the reason being that we have a higher DSCR right here is that we were constrained by our overall gearing ratio or leverage ratio of 80%. So if we were to lift this one up, let's go over to case 1 and actually increase our maximum leverage to say 90%. Execute our macro again. Then let's see what happens to our DSCR. At first, it's at a 1.3 flat from the first to the last period. And the very same output is generated for the loan life coverage ratio. And here you can see how well correlated the LLCR is, which essentially just looks at the full financing tenor holistically, while the DSCR only looks at the current period. So let's undo the leverage ratio change for now. I think conceptually it's clear how DSCR and LLCR correlate. Hit the master macro again, move over to the operations sheet. You will also notice that our min LLCR is given right here as well, and the min date when that min LLCR occurs is also calculated with an X lookup. Great. All right, guys, this was it for the LLCR. And in the upcoming lesson, we will implement our last missing piece for our senior debt section, which is our debt service reserve letter of credit. All right, I will see you in the next lesson. See you there.